Good evening and welcome to the Beyond Center's February Ask a Physicist. Before we get started, I have just a few quick announcements. Before last month's webinar, we announced that Paul Nurse would be giving the Beyond annual lecture on March 24th. And this month, we would like to announce that there will be a panel discussion with leading ASU researchers after Dr. Nurse's lecture. And anyone who registers for the lecture is welcome to attend that panel discussion. The registration link will be going out this week, so be on the lookout for that in your inboxes or on the Beyond Center social media accounts. Next month's Ask a Physicist will be on March 29th at 6 p.m. Mountain Standard Time with the question, can computers be conscious? So mark your calendars and also be on the lookout for that registration link over the next couple of weeks. Lastly, before we get started, I just want to remind everyone that if you have a question during the webinar, you can use the Q&A function within Zoom to ask that. And I will now turn it over to the moderator for the evening and the Beyond Center's Deputy Director, Sara Walker.
Thanks, Jessica. Hi, everyone. Welcome to this installment of Ask a Physicist. We're very excited to have you all here tonight and are looking forward to your questions. For our new guests this evening, our typical format is to have our two speakers present their views on the question of the evening and then open up to audience questions. You're welcome to enter your questions at any point during either presentation, and I will read through those questions to our speakers when we get to the open Q&A session after they've both had a chance to present their case. And tonight we're going to be talking about dark energy, and I'm going to pass it over to my colleague Paul Davies to present first. He is the director of the Beyond Center for Fundamental Concepts in Science, a world-renowned cosmologist, and a leading thinker in many areas. So it'll be very exciting to hear what he has to say. Off to you, Paul.
Well, thank you very much, Sarah, and welcome everybody. Let me just wrestle with the controls here because I have to share screen. And I don't know how to do that. It's not offering me the option. So this is a very bad start. Share. How do I share the screen? I think, Jessica, do you have to enable me to do that? I don't see a share screen command.
Paul, it should be at the bottom of your screen.
Yes, where? The bottom left, bottom right?
Bottom middle?
It's not offering it. That's a bit of a disaster.
We could have Maulik present first, perhaps, Paul, and you and Jessica shoot.
I think it would be better around this way. You are the host now, or maybe that makes it heavens. I thought we were on top of this technology. I do apologize to the audience. Bear with us. Let me just take this out altogether. There's nothing in the Zoom to say share screen. Bit of a loss to know what to do. There's a more command at the bottom.
Well, this is a good opportunity for our participants to brainstorm their questions. I already see some coming. So if you came in with questions, now's the time to enter them if you had them ahead while we're getting set up.
I can only think that I'll just come out of Zoom and just go back in again and see if it offers me the right thing. So just bear with me then. I don't even know how to get out of Zoom now. It's just the screen is so now I've got it. Okay, well, for future reference, you have to go to the full screen to see the command. If you're on the diminished screen, scaled down screen, it isn't there. So without further ado, can you confirm that this is looking okay?
Looks great. Thanks so
All
much.
right, all right, right. Well, let me apologize once again for my ineptitude. I'm not exactly new to these Zoom things, but I can still catch it out. Anyway, to business. So we're going to be talking about dark energy. What is dark energy? And my story begins appropriately enough with a pandemic. In the year 1665, Europe was struck by an outbreak of the bubonic plague, far more deadly, I might say, than COVID-19. And there were many towns and cities that were quarantined, and one of these was Cambridge in England, where the young Isaac Newton was working, and he decided to return to his residence in Lincolnshire, his rural residence, and self-isolate. That was very successful. Successful in as much as he escaped the plague, but also that's where he did, if the folklore can be believed, his legendary work discovering the law of gravity. And it's said that he got the idea from seeing an apple fall. I must admit this slide is very misleading. Almost certainly the apple would have been a Granny Smith, which is green and not red, but I hope you'll forgive me. Anyway, he applied the law of gravity, first of all, to the solar system and correctly explained the shapes and sizes of the planetary orbits. But he was also interested in the organization of the universe as a whole. And his law of gravity, let me remind you, is that every object in the universe is pulling on every other object with a force that's inversely proportional to the square of the distance. And the big problem for Newton was, well, what was to prevent all those stars out there from falling together into the middle, collapsing into one great mess in the center of the universe? And he came up with a neat solution. He decided, well, if the universe was infinite in spatial extent and the stars were distributed at roughly the same density everywhere, then any given star would be pulled equally in all directions. And so these forces of gravity would balance out. However, there was something of an intellectual sleight of hand, as he himself recognized, because to prevent this collapse, he said, I reckon it's as hard as to make not one needle only, but an infinite number of them stand accurately poised upon their points. We might say that it's an unstable equilibrium an infinite number of times. And so this lay like an inconvenient truth in the heart of cosmology for 200 years. Why didn't the universe collapse under its own weight? What was holding it up? What was shoring it up? What counterbalancing force could overcome the mutual gravity of all of the objects in the universe? Well, then along came Albert Einstein in 1915 with a completely different theory of gravitation, the general theory of relativity. This is not the place to do a tutorial on it. I simply want to point out that as a result of this general theory of relativity, it was possible for Einstein, who also puzzled over why the universe didn't collapse, to come up with a novel solution. And he did this by adding an additional term to his gravitational field equations. I'll come to that in a moment, but let me just say that in spite of the fact that this was 1915, nobody then knew that the universe was expanding. So Einstein, like Newton, assumed that it was overall static, and therefore there was a problem about collapse. So what Einstein did was introduce an anti-gravity force that grows with distance, a cosmic repulsion term in his field equations. So normal gravity diminishes with distance, but the cosmic repulsion or anti-gravity grows. And by choosing the numbers correctly, he could get the two to balance each other and produce a static universe. So for Einstein, at that time, the universe didn't collapse because it was propped up by this anti-gravity force. Because it grows with distance, it gets very large on a cosmological scale, but almost completely negligible on a terrestrial scale. So, wouldn't be much help for would-be levitators, the it represents about 10 to the minus 26 grams reduction in weight. Now, these are Einstein's gravitational field equations, and it doesn't matter if you don't understand them or you never come across them. So for the benefit of the non-physicists in the audience, this is what they look like. And the main thing is that this is a simple equation with very few terms. In fact, it's even simpler if there is no matter there. It's just empty space, because it just reduces to the equation R equals 0. Now, there's a story that Richard Feynman used to like to tell, that his father thought, well, his son was a famous Nobel Prize winning physicist, perhaps he should learn some physics. And so he said to Feynman one day, I've learned the vacuum Einstein equations, R equals 0. And Feynman said, well, that's great. And his father said, all I need to do is figure out what R is. So anyway, it doesn't matter for these purposes, because what Einstein did in order to get his anti-gravity was to add this additional term to the field equations. And that has the effect of causing a cosmic repulsion. And in effect, it describes the phenomenon that space is self-repulsive. If you take all the matter away, and the matter is on the right-hand side of this equation, if that was 0, that space just repels itself, and so it expands and expands and expands in an uncontrolled way. And Einstein could get a static universe by balancing that innate tendency for space to just expand itself against the weight of all the material in the universe. But just with Newton, it was like balancing a needle on its head, on its point. It was unstable, an unstable equilibrium. And Einstein traveled to the United States. Some years after this, met Hubble, discovered that the universe was in fact expanding, and realized that this was a terrible blunder, trying to introduce this cosmic term to get a static universe. Had he not done that, he would have realized that the universe would either collapse or must expand. It would have to be moving, and he missed that particular trick. But ironically, it turns out that he was probably right all along, because in the late 1980s, it was discovered that the expansion of the universe was actually accelerating. It's picking up in speed. So it's not a constant acceleration, nor is it a slowing acceleration, as we used to believe when I was a student. It's actually an accelerating expansion. And I'm showing a picture here of Brian Schmidt. He was one of the astronomers who made that discovery. And I'm showing his picture alone because, as far as I know, he's the only Nobel Prize winning astronomer to be president of a university. In this case, it's the Australian National University. The situation we now believe is that there was a Big Bang, the universe decelerated, then there was a sort of gigantic cosmic tussle where the forces of attraction and repulsion were sort of slugging it out, and the forces of repulsion, the anti-gravity force, eventually came to dominate, and the universe is now speeding up. So we're in that speed up phase where anti-gravity is dominating the expansion and will only become more dominant in the future. So now, how are we to think of this physically? Because I'm using the term anti-gravity, but it became fashionable to call it dark energy about 30 years ago, maybe 40 years ago. Why dark energy? Why energy? Why dark? Well, dark, partly because we don't see anything, but also because it's said to be mysterious. And so it's known as dark energy. But Einstein's anti-gravity force, his cosmic repulsion, was a description of precisely what is going on. I just want to make the case that I think that's all we need. Now, why would, I say it's dark energy, why would empty space have energy? The dark energy is really just the energy of empty space. I mentioned that if there's no matter present, space self-expands, it self-repels, it just goes on swelling. as a result of this dark energy. But why should there be any energy in empty space? And one answer comes from, it's the weight of matter. What's that? One answer comes from quantum physics. You have to look very carefully here. Physicists know that empty space, the vacuum, is not actually totally empty. It's full of activity in which particles come into existence very fleetingly and they disappear again. It's called virtual particles. There's a fair amount of activity. Quantum frolic, I'm calling it here. If you look very carefully, you'll see some particles appearing and disappearing. And this is going on all the time. And there's a certain energy associated with that activity. And theoretical physicists can calculate how much energy there is in empty space, in the vacuum. Now, you might think, well, why can't we just measure it? Well, it's very difficult to measure the weight of space because it's everywhere. You can't sort of get space inside a box and not have it, and put it on a balance like this and not have it elsewhere. So we can deduce what the weight of space is from the rate of expansion of acceleration of the universe. But can we compute it from fundamental theory? Well, we can. I had a go myself many, many years ago. The problem is that you come out with a number that is completely ridiculous. 10 to the 90 grams per centimeter cubed is the mass. The measurement is more like 10 to the minus 30. So this is out by 120 orders of magnitude, which Stephen Hawking called the greatest failure of theory known to science. And so this is a sort of spectacular example of how we have a good way of explaining this, what's going on with this cosmic repulsion, but the numbers have never been more wrong. However, just I'll throw this in for good measure, maybe 10 to the power minus 120 isn't so odd after all, because it is just the cube of the ratio of the force, the gravitational force to the electric force in the hydrogen atom between the proton and the electron. That's about 10 to the minus 40. So maybe if we had a theory of fundamental forces, a theory of coupling constants, there would be some numerology going on that would make 10 to the 120 a very natural number to come out. So that's just a thought I would leave you with. To put this in perspective, 100,000 cubic, a cube, 100,000 kilometers on the side, contains just about 1 gram of energy. Now, one final point, I talk about dark energy. Why does it anti-gravitate? Energy, after all, is mass equals mc squared, and mass is supposed to gravitate, not anti-gravitate. Where does the anti-gravity come from? Just very briefly, why anti-gravity? So for Newton, mass is a source of gravity, and it is also for Einstein's theory. We know from the E equals mc squared that energy will also gravitate. Energy has mass, so it gravitates as well. No problem at all. But in the theory of relativity, space and time become coupled together in a way that they can't be separated. They're intimately interwoven. And conversely, not conversely, but as an adjunct to that, energy and pressure also become entangled with each other. And so if energy is a source of gravitation, then pressure must be a source of gravitation as well. And that's the situation in the general theory of relativity. Pressure gravitates. We don't normally notice the gravity of pressure. We think of pressure as a pushing force, and indeed its mechanical effect is to cause things to expand, but it does have a gravitational effect that is a pulling force. The gravitational effect of the pressure inside the Earth, for example, contributes about 1 billionth to your weight. But of course, pressure means more gravity. What we want to get anti-gravity is negative pressure or tension. Negative pressure is a well understood concept. And when you look at the at empty space, what you find the cosmological constant, the lambda constant, it represents a negative pressure or a tension, which is a factor 3 greater than the energy. So there's dark energy there, but there's 3 times as much negative dark pressure. And so that wins out. And that means that anti-gravity triumphs over gravity. The best way I can express this negative pressure is saying that space sucks. And if you want to know by how much does it suck, it's 100 trillionth of an atmosphere worth of sucking. And that's sufficient to propel the universe into this accelerating expansion. It's going to finish with a pie chart and then hand over to Maulik. The total amount of energy in the universe, of mass energy in the universe, is dominated by this dark energy, about 3/4 of it. There's another component which we're not talking about here, which is dark matter, very important subject. That's for another occasion. And then normal matter, the stuff of which you and I are made, is a paltry 4% of the total mass of the universe. So it's almost like we're a cosmic afterthought, and almost everything is in the form of this dark energy. But what is dark energy? I think it's probably nothing more than Einstein's cosmological constant introduced all those years ago, back in 1917. I think we don't need any more than that, but many of my colleagues, theoretical physics colleagues, think there's something deeply mysterious about dark energy and that it must be some additional type of field or something that would have strange properties. So to find out a little bit more than that, I'm going to stop talking and hand over to Maulik. And I'm sorry about the hiccups at the beginning. I will get better at this over time. I'm going to stop screen sharing now.
Thanks so much, Paul. That was great. So please remember to enter your questions in the chat and we'll get to them after Maulik's presentation. So it's my pleasure to introduce Maulik Parikh, who is a cosmologist and theoretical physicist at Arizona State University. And Maulik, I'm going to pass over to you.
Right, thanks. Can you hear me? Great. All right, hopefully you can see the screen now. Let's see. Right, so I want to tell you about, well, Paul has already told us a little bit about dark energy, and I want to say—
full screen, Maulik, because I think we still see your sort of slide reel. I don't know if you can make it full screen.
Sorry, what's happening?
Can you make the slides full screen?
If I make the slide full screen,
you just have to go to slideshow and, from the beginning.
Okay. Sorry, let me start that. Let me do that again. I thought I could avoid some technical problems, but
not doing too well today, are we?
Okay, and
our audience will show up for the next one in 1 month's time.
All right.
You've got a month to practice how to get this right.
Is that better?
Yep. No. What's wrong if you just go to slideshow?
Is this full screen now?
No.
Is this full screen now?
It's not.
What do you mean it's not? What do you?
Well, we're seeing, if this is a PowerPoint presentation, we're seeing the whole PowerPoint file there, not just the presentation itself.
So Maulik, we see your slide large, but there's also sort of the slide reel on the side and some of the headers for, I think it looks like you're using Keynote along the side.
I am.
Yeah.
Okay, I don't know how to, why don't we just ignore it?
What about if you go to view at the top?
We can still see your slides, so that might be okay, just in the interest of time, so we have enough time for everybody's questions.
Oh, okay.
Left, yeah.
View now, slide only. How's that? Is that better?
Yes.
Okay, let's try this. All right. Okay, so I want to tell you a bit more about dark energy, but I'm going to focus more on the implications for the fate of the universe, because in fact, what dark energy is going to affect the ultimate outcome for our entire universe, quite likely. So as Paul already mentioned, dark energy comprises most of the energy of our universe. And these are the updated figures from the European Space Agency's Planck mission. And we see that dark energy is about 68% or so of the energy budget of our universe, and with another 26.8% given belonging to dark matter, and only about 5% of the universe consists of the kind of matter that we ordinarily think of as matter. Things that are made of atoms, like us and stars and everything in the periodic table of chemistry. So everything we learn in chemistry is only a tiny sliver of what actually the energy, what actually are the ingredients of the universe. Now, I want to make a distinction, however, between dark matter and dark energy. Dark matter, we don't know what it is, just as we don't know what dark energy is. Both are dark. They interact, which means that they're pretty much invisible. They interact very weakly with light. But that's where the similarity ends. Dark matter is very easy to understand. I mean, we don't know what it is, but we can easily imagine that it's just some unknown new kind of matter, new kind of particle that we haven't discovered yet. We discover particles all the time. Maybe it's something called an axion or a neutralino or something. And we just haven't found it. And maybe one day we'll discover it in our accelerators or in some other way, and then we'll know exactly what it is. But dark energy is something completely different, and it has some truly mysterious and puzzling properties that are very unlike atomic matter as well as dark matter. So what do we know so far? Well, we know very little. We know that it's invisible. Okay, it's dark. We know that it causes anti-gravity. That's already different from dark matter. So somehow dark energy is causing the accelerated expansion of the universe. Instead of the universe slowing down as you might expect from gravity, as the galaxies get further and push out, they attract each other back and collapse on themselves. Instead of that happening, they're speeding away ever faster. And also another feature of this, which may be related, is that dark energy does not dilute. So what does that mean? So imagine if you have, I don't know, a dozen batteries or so. So there's a certain amount of energy in each battery. You have a dozen batteries, and you put them in a box. You cram them in a box. So now the back box has an energy density because you've got all that. You've got all those batteries packed in there. Now, if you take the same dozen batteries and you put them in a much bigger box, the total energy is still the same. It's just the same amount of energy stored in those 12 batteries. But now they're spread out over a much greater volume. The box is bigger. And so the energy, although the total energy is the same, the energy density becomes diluted because the box is bigger. Okay, so the average energy density will go down as you increase the size of the box. That's how most matter works. It works for batteries, it works for atoms, it works for light even. And as the size of the box, as the size of the universe increases, whatever energy is in it gets diluted. But that's not true for dark energy. Dark energy does not dilute. It just stays, the energy density stays the same, which means that if the volume goes up and the energy density is the same, that means the energy is actually increasing. The amount of energy in the
Maulik, sorry to interrupt. I think that your slides haven't been changing, so I'm not sure which slide that you're supposed to be on, but we haven't been seeing the image. We just see still the title slide.
That's all right. That's what it's supposed to be.
Oh, okay, double checking. Okay.
Yeah. So the energy will increase because the energy density stays the same as the volume increases. All right. So that's very unlike anything that we've seen so far. Okay, so we want to understand what this could be. Well, so what could it be? There are a few, we actually don't know anything that behaves like this, but there are a few candidates. These are all theoretical candidates. And one possibility, which is perhaps the most likely one, is something called the cosmological constant or vacuum energy. In gravity and in quantum mechanics, the vacuum, which you would think of as empty space and has can actually have energy. It's not, you might think that just if there's nothing there, how can there be any energy? And that common sense intuition is actually wrong. The vacuum is a very lively place in quantum mechanics with particles being created and destroyed fleetingly and they average, although every pair of particles that's created lives and dies in a split second, there's always some of them present, and so that together they have some energy. The only problem with this, as Professor Davies already mentioned, is that the theoretically predicted value of the vacuum energy is vastly higher than what we actually observe. So although we have an argument for why it could be vacuum energy, it doesn't work out at all in mathematically. There's also another hypothetical possibility called a quintessence field. A quintessence field is a kind of a new kind of medium that permeates all of space. In this case, it depends on time, and if dark energy is quintessence, then its properties would change in time. And an example of a special case of that quintessence is something called a phantom field, which is a very extreme form of dark energy in which the universe is not only accelerating, but accelerating ever faster. Even the rate of acceleration would be increasing, it will increase in time. Okay, so those are some possible suggestions for what dark energy could be, but they all have theoretical problems, and we actually don't know which one it is. So this is really one of the great deep mysteries of theoretical physics. And maybe it's also kind of an embarrassment, because this is the dominant content of the universe, and we don't know what it is. So, as I said, there are different, depending on what dark energy is, the fate of the universe could be quite different. And there are sort of 4 ways that the universe might, meet its demise. They're called the big freeze, the big rip, the big crunch, and the big bounce, in contrast with the big bang, which is how the universe came to be. And so I'm going to describe these 4 scenarios one by one. All right, so what is the big freeze? Well, the big freeze is not what's going on in Texas right now. This is something a little bit different. The big freeze comes about as follows. When you have all these galaxies, remember the dark energy causes ever expanding, ever greater acceleration. So clusters of galaxies accelerate away from each other. They're repulsed by the anti-gravity of space until they're so far away that their light cannot even reach us. So imagine we're here in our cluster of galaxies in our Milky Way, which is our galaxy and our local cluster of galaxies, and all the other clusters of galaxies have sped away because the space between them has swelled exponentially, and they've basically just disappeared. There comes a point where they've gone so far that their light cannot even reach us in principle. They would be beyond the event horizon. And so then we would be left with only our neighboring galaxies, the Andromeda galaxy and some other nearby galaxies, and it would be just us in the entire universe, with all the other galaxies having escaped out of our visible universe. And eventually, our handful of galaxies the stars in them will burn all will exhaust their fuel through thermonuclear fusion. And then they will die and they will collapse and form black holes. But even these black holes are not immortal because according to Stephen Hawking, the black holes themselves will eventually evaporate. They'll disappear in a kind of a mist of Hawking radiation, as it's called. These are little particles that peel off the black hole until the black hole is gone. And finally, all we'll have left in our universe will be this sea of cold and particles, and so it'll be cold and it'll be empty in the sense that they won't even be atoms. They'll just be these subatomic particles floating around, and so the universe will be devoid of life, atoms, or usable energy. So this would happen in about 100 trillion, well, depending on the scenario, between 1 and 100 trillion years from now. So it's really an extraordinary extrapolation, and we really have to have a lot of faith in our laws of physics to predict that far ahead. But our current equations point to this scenario. This is the most likely scenario, and it's actually quite it means that future astronomers when even before the universe turns into this sort of frozen heat death, will think that the neighboring galaxies is all that there is, and only now. So we live in a kind of fortunate time because we know that there are many galaxies out there, and the full rich structure of our universe would be hidden from future astronomers who just would never learn about it. So that's the big freeze. Another scenario.
Maulik, I'm going to interrupt again because we're still not seeing slides change, and I have a feeling at this point you're probably trying to change the slides.
Wait, are you serious? You're not seeing the big freeze?
Oh, now we see it.
Okay, let me just keep it like this.
Okay.
Can you see the big freeze here?
Yep, you can see it now. Thank you.
All right, so you missed my, okay. But now I can't go to the next slide. Okay.
Yeah, perhaps you should just show the slide deck on the other side, and then we can make sure
this
that.
was my previous slide.
Your Texas freeze.
That was a joke. All right, and so here was okay. So these are the 4 scenarios that we had, and I'm going to go describe them one by one. So this is the big freeze, and now the second possibility is something called the big rip, and this is an extreme form of dark energy due to a field called the phantom field. And this is a hypothetical field which with ever accelerating repulsiveness. So remember that dark energy is an outward force that overcomes the attractive force of gravity. So this is something that is the opposite of that. It's very if dark energy is this phantom field, then its strength, its repulsive strength will grow and grow until it overcomes not only the weak gravitational attraction, but even all the other forces too. So for example, it would tear apart galaxies, but it would even tear apart atoms, because think of an atom. An atom has a proton and an electron, and the protons and electrons attract each other through the electromagnetic force. And if the phantom is powerful enough, as it grows in strength, even that electromagnetic force would not be enough to hold the atom together, and the electrons will be ripped apart from the nucleus. But then, as the phantom got even more powerful, it would overcome even the strong nuclear force that binds the nucleons together, and they would break up into quarks, and we would basically destroy all of matter as we know it. So that scenario is called the Big Rip scenario, and here's how it would go. We'll sort of end in about, the prediction is it'll end in about 22 billion years from now. Okay, so here's the timeline. We are at the bottom of this Big Rip, and about 60 million years before the Big Rip, so in other words, 60 million years before that, 22 billion years from today, the Milky Way will be destroyed, and then as it gets more and more powerful, ever smaller systems break up, the solar system, the Earth, and even atoms. So that scenario is known as the Big Rip scenario. Finally, well, not finally, the third possibility is the idea that dark energy actually goes away. All right, so it turns out to be something fleeting. We only think that right now it's dominating our universe, but maybe it will just fizzle out somehow. And then in addition, if space is finite, then now there's no more repulsive force, and there's all this stuff in the finite space that'll attract each other back through gravity. So that'll cause the universe to collapse back on itself, because now that the anti-gravity is gone, all you'll be left with is gravitational attraction. And in this scenario, the universe will end with a big crunch, which is sort of the mirror image of the Big Bang. So we'll again have a kind of fiery explosion at the end. Not an explosion, but an implosion. This scenario is not very plausible because, well, it could happen, but it requires a few things that at this moment in time seem unlikely. Noted in particular that dark energy could disappear, and also that space is finite. We don't know whether space is finite or not, but dark energy, it's hard to imagine how dark energy could just go away. Then there's a variant in this which uses dark energy, and which is sort of a kind of a has an element of reincarnation in it. In this scenario, the universe does collapse back in itself if there's a big crunch, but that big crunch is followed immediately by the big bang of a successor universe. So you go through this endless cycle of universes being born through big bangs and dying through big crunches, which are and each death of a universe is the birth of the next one. And a modern version of this involves extra dimensions from string theory. The universe as we know it could be on these. There could be a pair of universes, okay, each one living on a imagine these sheets, and in each of these universes there's dark energy on that dilutes everything away until until the sheets become flat, because all the interesting stuff is gone and it's just plain and empty. It's just boring and empty. And then they collapse on each other through their gravitational attraction, and that collapse of two entire universes colliding with each other causes something cataclysmic, and that's basically the end of those two universes, and at the same time the birth of two new ones. So this is called a cyclic universe, and in this model, unlike in the big crunch scenario, there's dark energy plays an important and essential role. Okay, so I'll stop here and let me just leave you with a poem from Robert Frost about the various ways that the world can end. Thank you.
Thanks, Maulik. That was great. So we'll leave the poem up for a minute for people to read. And I'm going to start going through some of the questions that we got in the Q&A and also questions that we received ahead of time. So there's always an opportunity with these Ask a Physicist events for you to send your questions in ahead. So the first question I am going to take in the Q&A comes from James Benford, and it's, could dark energy be due to space-time being a different shape than we think?
I can take that.
Dark energy with all different shapes of the universe, so there's sort of.
Oh, let me switch off my sound.
Paul, it's hard to hear you.
Oh, I'm sorry. The shape of the universe and dark energy are really sort of separate things. However, I should say that if the universe is spatially closed, there is a contribution to the quantum vacuum from that closure. It's related to something called the Casimir effect. This is not the time to get into it, but that is not going to do it. When you actually do the calculations we've done in the 70s, it doesn't give you the right repulsive term. I know no more than that about the connection between those things. Oh, there's a whistling sound.
Excellent. Thank you, Paul. Okay, we will take our next question. This is one of the questions that came in ahead, and it comes from Tom Quake. And the question is, with an accelerating and expanding universe in dark energy, how does Hawking's concept of zero energy deal with the cause of the acceleration? What is the cause of the push away from zero to create dark energy in an accelerating way? And this is in reference to Stephen Hawking's book, The Theory of Everything, in 2002. Maulik, do you want to take this one? Oh, you're on mute.
I'd like to say something more about the previous one, actually.
Okay.
So the previous question was about the shape of the universe. There is a sense in which vacuum energy depends on the shape of a box. If you take a box and you put an empty box, the amount of energy in it depends on the shape of the box. That's called the Casimir energy. And it's possible that if dark energy is vacuum energy, then it does depend on the shape of the universe. And there are some nice examples in which that dark energy, in which the shape of the energy can change, and the dark energy can change in response to the shape changing.
Excellent. Thanks, Maulik. So just back to Tom's question about if Stephen Hawking's proposal, the total energy of the universe being exactly zero, what that implications of that are for the acceleration.
It is zero even with the acceleration, because the way you know that is because of the geometry of space. On the large scale, the universe is flat, that is, its geometry is Euclidean, and that goes with the total energy of the universe being zero. We're talking about dark energy is one component that makes up the stuff of the universe. When you look at it all and take everything into account, it comes out to be zero. And that's one reason that we don't worry too much about the universe coming from nothing, because it doesn't need any energy to get going.
Excellent. Thank you, Paul. Okay, our next question is from Barbara Temple. And this was asked in the chat. It's an excellent question. Does dark energy break the first law of thermodynamics?
Well, yeah, Maulik actually dealt with this, didn't you? That it just goes on replenishing and replenishing. And
yeah, actually, it does obey the first law of thermodynamics, but it obeys it. So the first law of thermodynamics relates energy change with volume change and with work. And so here what happens is as the volume increases, so does the energy. So it does obey the first law of thermodynamics.
It's because of the negative pressure, it does negative work. And so as you get a volume of space expanding, there's more energy in that expanded volume. But if you just regard it like a gas in a cylinder or something, then it will do negative work, and so it all comes out to zero. It's as Alan Guth, who first invoked the idea of anti-gravity as an explanation for the Big Bang, the so-called inflationary universe scenario, said it's the ultimate free lunch. You just go on getting more and more space, and that space is filled with more and more dark energy, but it still all adds up to zero.
Free lunches forever. Okay, so there's two related questions in the chat. The first, so I'm going to ask both of them. I think you can answer both at the same time. The first comes from Javier Margrina, which is there dark energy in the human body? And the second is from Julie Rose Black, which is dark energy something that only exists out in space, or is it also on Earth?
Yes, you may miss my slide of the levitating lady. So it's certainly, it's in us and all around us. Space is everywhere, and wherever there is space, there's dark energy, but not much on a human scale.
Yeah, that's very unlike dark matter. There's certainly not dark matter inside us.
So we've had some questions about dark matter. It's a totally different topic, and the word dark,
So dark matter is just some different type of matter that's not atoms, and as far as we can tell, it's not. There's no such matter in us. But dark energy is this energy that seems to permeate all of space, and since we occupy space, it's in us as well. And the phantom, the big rip scenario with this crazy phantom dark energy, that really the kind of horrible effects of destroying atoms and so on that happen are precisely because that phantom energy is everywhere. And so even within a nucleus of an atom, it's there and it's tearing everything apart.
Great. So this question probably both of you can answer. So we were presented many scenarios for the end of the universe, but Parker Sorge would like to know, which of the four fates of the universe do you believe is the most likely to happen? So perhaps we can get both of you to answer. That'd be great.
Well, let me evade the answer, but by pointing out something which is really problematic with the question, and that is this: that if dark energy is constant, then Maulik has explained how the universe will end. But supposing it deviates just an infinitesimal amount from being constant, we may never know that for trillions and trillions of years. And so it's impossible to actually say the ultimate fate of the universe. You might live, or society, descendants may live for a trillion years and still find no evidence of a departure of the dark energy from constant value. But that it could be just changing very slowly over some longer period of time, and that would lead to the other outcomes, the crunch or the rip, and we just can't know it. So in a sense, it's an unanswerable question.
Well, I think it's unanswerable. It might be unanswerable observationally, but theoretically, if we knew what dark energy was, theoretically, if maybe there was some theoretical reasons for expecting dark energy, perhaps from string theory or something, some more fundamental theory, then we would be able to say which of these outcomes would be realized. I can say that the phantom one seems really far-fetched to me. The kind of properties of that field violate a lot of the kinds of laws of physics, and I think, although you know, I mean, maybe 10, 15, I don't remember when, but a couple of decades ago, it was a big topic because it's just because it's such a wild idea. I don't think it survived close scrutiny. So I think we can rule that one out. The cyclic universe one also has some problems. In particular, theoretically, it's not clear how to go from the Big Bang to the Big Crunch. Sorry, the Big Crunch to the Big Bang. And also it assumes some features of these brains, which are these surfaces that live in an extra higher dimension, which could be there. I mean, it's kind of speculative scenario that is inspired by string theory, but it's not directly predicted by it. So again, that one looks a bit doubtful. The idea of a big crunch requires that the universe really not have dark energy, actually, which at present observations indicate not only it's dark energy there, but it's the dominant energy in the universe. So I think that the most likely scenario is, unfortunately, that the cold, empty universe, the big freeze, where there'll be nothing left, and that's kind of a sad and
well, it's a shame to leave on a depressing note, and when I write about this topic, I point out the fact that sufficiently advanced technology could engineer a baby universe to set the whole cycle off again, and we could decamp to it through some sort of wormhole and leave our one to its miserable future.
Maybe, yeah. That's an interesting idea.
Do we have any more, Sarah?
Yep, I have lots more. Sorry, there was.
We started late, so we should go on a little bit after.
Yeah, we have a few more minutes. So this question's a little bit more technical in nature. It comes from Wayne Harrison, and the question is, how is a brain defined in the last case? So I think this was referring to your talk, Maulik. If you could explain what a brain is, that'd be great, in cosmology, in our minds.
So, all right. So it's always hard to imagine extra dimensions, but there's a trick to it. So the trick is that instead of thinking of what the fourth dimension looks like, which is pretty much impossible, we should imagine what the third dimension looks like to two-dimensional beings. So if we were two-dimensional beings, if we lived in a two-dimensional universe, the third dimension would be to us, to these two-dimensional beings, what the fourth dimension is to us actually right now. So imagine then that we are two-dimensional creatures that live in a two-dimensional world, in a two-dimensional universe that is that's basically a sheet of paper. So that's what a brain is. It's a kind of sheet of paper or a surface that exists in a higher dimension. So there's an extra dimension. So our universe would be like flies stuck to fly paper, and that would be our world, our brain. Brain is short for membrane, and there would be an extra dimension perpendicular to us that we couldn't point to because we could only point in our two dimensions, and somewhat away in this extra dimension is another sheet of paper where another universe lives. And if these two collide with each other, then throughout each of these universes, there would be this cataclysmic event, and that would be a big crunch.
Excellent. Okay, so since there's been a little bit of confusion about dark matter and dark energy, and we've touched on that briefly, I'm going to take one question next on dark matter, which comes from Vince. And the question is, how do we know that dark matter is not simply non-radiating conventional matter?
Did I go that one? It's certainly true that there is a lot of just plain dark things out there, like black holes, for example, an obvious example. But the way in which you know there's an additional component comes from looking at the details of the Big Bang, the nucleosynthesis, and the fluctuations in the cosmic microwave background came out of the Big Bang, and putting it all together to make a consistent story. And there has to be a technical term, there's some sort of non-baryonic component. So it has to be something which doesn't make up atoms. So you get it from looking at consistency with this bigger picture. I don't know, Maulik, do you have anything to add to that?
Yeah, this was actually a viewpoint that, a very conservative idea that maybe dark matter is nothing special. It's just dim matter. It's something we can't see with our telescopes because it's just not emitting enough light, and it's just some plain old boring thing like a bunch of, very dim stars or something. But that idea has been pretty much ruled out. I mean, first of all, we know the distribution of dark matter, and it's around galaxies there are halos, and those halos are where the dark matter resides, and that's not, whereas the ordinary matter lives somewhere else. It's actually, even in space, it's not in the same place. It's not found in the same place as ordinary matter. So we think it's something different.
Excellent. So we have a question coming in from Prabhu Barathan on the ultimate cause of the beginning of the universe. So this is related to Paul Steinhardt's published paper about the possibility of a cyclic universe. And the question is, isn't that more feasible as it gives rise to existence before the mythical Big Bang, quote unquote, that is ever puzzling to cosmologists? We do observe cycles of time such as months, years, millennia, etc. Why cannot that be applicable to the universe too?
Okay. Whilst you deal with your childcare issues, Sara, I will take this up because I've been interested in this topic of the cyclic universe for my entire career. And it's not a new idea. In fact, within the context of general relativity, it was discussed at great length by Richard Tolman in the 1930s. And the point is that with the cyclic universe has to do with the second law of thermodynamics. The cycles, if you just take the simplest thing of a universe that collapses to a crunch-like state, it's actually a big bounce, and everything goes through into the new cycle. The entropy still goes on getting bigger and bigger. And what Tolman showed was that the cycles get longer and longer. And so you don't actually have true cyclicity. There is still a progress. So there's still a problem about the ultimate origin of the whole system. So I don't think you escape that. And in this new version by Steinhardt or any of these other versions of cyclicity, you still have the problem of the ultimate origin of things and the problem of whether the entropy from one cycle gets through to the other. Now, if you erase all records, if the effect of, say, the crunch is to erase all information about the preceding cycle, then it makes no real sense to say that one cycle comes after another because everything is gone. These are just independent cycles. So there are deep philosophical problems either way, I think, to having a cyclic universe. Maulik, you may feel different about it.
Yeah, I think the cyclic universe of Steinhardt has a clever way to get around the entropy problem. So entropy is a measure of the disorder in a system, and there's this kind of almost ironclad law called the second law of thermodynamics, says that the universe becomes ever more disordered and chaotic and messy. So what happens is, and that's true, but because of the expansion of so as the universe gets messier and messier, but because of the expansion of the universe, all that mess is sort of, if you like, diluted by the expansion of the universe. So although the total entropy is going up, the entropy density, the messiness per volume, actually can go down again. And that's possible if the universes were infinite. So there is a kind of a loophole in which these universes can go from one to another with the entropy increasing throughout without reaching a sort of conflict with the second law.
Maulik, you have to assume that the cycle time is longer than the evaporation time of the largest black holes. Otherwise, if the black holes get through, that's a form of entropy from the previous cycle.
Yeah, I mean, there are other issues there with. I think my main problem with the cyclic universe is that, well, it's a pretty picture, but there are no equations that actually take you from one universe to the next.
Thank you both for that. So since we had technical issues, I'm going to run to about 5 after. Typically, we would end right on time at 7 o'clock, but we know that we delayed a little bit of time and we lost some time this hour. So we have time maybe for 1 or 2 more questions. The next question I'm going to ask comes from Peter Klupar, which is, what is the next best answer besides dark energy? Is there another answer?
Yeah, some people have tried to account for the observations differently. I should say that there is one thing that's always troubled me, that the observations of the accelerating expansion come from looking at type 1a supernovas. These are a particular type of exploding star, on the assumption they provide a standard candle, that is, that they're a constant intrinsic brightness, and then you count the distribution in space. But can we be absolutely sure that over the history of the universe, that the brightness of the type 1a supernova hasn't changed slightly and skewed those results? I've never seen that addressed. I've mentioned it a few times, because after all, the material in the stars is changing as the heavier elements accumulate, the so-called metallicity stars. So maybe that will affect the intrinsic luminosity of type 1a supernovae, and it'll turn out that these observations are misleading.
Thanks.
Yeah, there's one, well, so we infer the existence of dark energy because of observations we've made about the way that the universe has been expanding. And those observations are then fed back into Einstein's equations for gravity, and we therefore conclude that that Einstein's equations had that there was some dark energy living there. But it could be, although it seems hard to imagine how this would work, it could be that what's actually wrong is our understanding of gravity. That maybe and this is one approach that people take particularly for dark matter. So instead of concluding that the strange behavior of strange motion of matter is explained by a new kind of matter, dark matter, we say the strange motion of matter is explained by changing our theory of gravity. But that's much easier said than done. So
All right.
I would be very surprised if that were the point.
Thank you both for that. Since we have just about a minute left, I think I'm going to wrap up the Q&A session, and want to thank you both again for the excellent summaries of all the latest and greatest and how we're thinking about dark energy.
My apologies for the technical hitch.
Yeah. Thank you to all of our participants today and for all the fantastic questions. We hope you'll join us again next month, where we'll be discussing whether or not computers can be conscious. So we'll see you then. Thanks, everyone. Have a great night.